G'day viewers. In this segment we'll talk about wireless multiple access protocols. And yes, this is it. This is Wi-Fi, what we've been waiting for. So let's find out how it works. Okay, so our setting here is the same as the setting that we looked at in the previous lecture. We have multiple nodes, they just want to share a link. How do they do it? In this setting, however, the nodes are wireless, or the link is wireless and the nodes are using that wireless link. So we have 4 different laptops here, they're talking to an AP, they just need to decide when to send. Now, to understand the way the protocols work in this setting, what we're going to do is build on the schemes we used in our simple wired model. So all of that carrier sense multiple access stuff, that was more useful than just for classic Ethernet. We'll use it as a foundation to understand how 802.11 works today. Well, the first thing that you might ask is why wouldn't we just use some of the protocols we've seen before that were used for classic Ethernet? And the reason for this is that the wireless case is more complicated than the wired case. I say surprise here because this always seems to be the case for wireless. The way signals propagate across a wireless medium is much more complicated than sending signals down a wire. And that seems to have all sorts of implications for how you design the rest of the protocols for a wireless system. In our case, just thinking about multiple access, there are a couple of issues here. One issue is that nodes can have different coverage areas. When you send down a wire, if everyone's attached to the same wire, you expect that everyone on the wire can hear all of the messages. That's not the case with wireless. The nodes might be a fair distance apart, and so they might not be able to hear one another clearly. This will mean that our schemes such as carrier sense don't work very well. The second complication is that nodes can't easily hear one another while sending. There can be enormous differences in the power level between a signal that's sent and received. The received one can be so much weaker that it's difficult to hear both signals at the same time, so it's difficult to detect collisions. So we'll have to come up with alternatives to that. The bottom line here, you can see in the figure at the bottom, is just to remind you that wireless 802.11 does not operate according to CSMA-CD. We have to improve it. So let's see how we do that. Well, first we've got to go into these two issues. The first issue is the different coverage areas. Here's what's going on. In the figure here we have 4 different nodes, A, B, C, and D, and they're just spread out over space. Now the wireless signal is broadcast, and as it's broadcast it propagates over an area, it's attenuated, it can be received by receivers as long as the signal to noise ratio is high enough, and that's just within a region. So here it looks like A can send to a neighbor B that's adjacent to it, but A's signal can't be received by C. It's too far away, the signal's grown too weak, it can no longer be received. Similarly for B, C, and D, and this leads to different coverage areas. You can see the radio range here is indicated as just enough to get from one node to the next, but not a lot further. B, by the way, when it sends, its signal will be received by A, but also by C, because that's also within radio range. Different coverage areas lead to problems. And one of the classic problems here is something called hidden terminals. When you think it's okay to send because you can't hear someone, yet interference still results. So in this figure we have a hidden terminal situation when A and C are hidden terminals when sending to B. Let's see what happens. Now A and C, when they want to send, they cannot hear one another's transmissions. This means if they use something like carrier sense, they would listen and they would hear no one and say, okay, the medium is not in use, it's fine to send. However, if they both send at the same time, both of their signals receive at B, received at B, or arrive at B simultaneously. Those signals are mixed, superimposed on one another. The result is a jumble, 2 people speaking at once, so B cannot separate these messages and receive them. It's a collision, and we would like to avoid this because we've just wasted some of the resource of the link. We could have used it to deliver a real frame, instead we got a collision, and neither of the frames gets through. The second problem that arises because of different coverage regions is something that's called the exposed terminal problem. Now, exposed terminals are a situation when you think you have interference because senders can hear one another, But actually there is no interference at the receivers, so you would really like to send multiple packets at the same time. Here, B is sending to A, so B is sending to A there, and C is sending to D. And in this situation, they are exposed terminals. They're exposed terminals because B and C can hear one another. When they're sending, it looks like their signals will collide here. However, C's signal doesn't propagate all of the way to A. There's no problem here. So A will be able to receive B's signal cleanly. Similarly, B's signal doesn't propagate to D, so D will be able to receive C's signal cleanly. When this situation occurs, we would like to take advantage of it and have B and C send at the same time, because we'll get more performance out of the network. We can send two frames concurrently and get them both through the network. The second problem, the second complication for wireless had to do with the inability to detect collisions. And that's really because with wires we can engineer the relative strengths of the transmission and reception signals, so we can work out if both are going on at the same time. With wireless, there can be a tremendous difference between the power levels of the sent signal and the received signal, which might be 1,000,000 times weaker. This makes it very difficult to process them both at the same time. So essentially when you're sending, you're shouting and you're deaf. You can't hear if someone else is talking. With wires, we're able to detect collisions, and because of that we can abort the transmission, and this greatly lowers the cost of collisions. So you can see here the wired collision takes only a very short amount of time. It happens, everyone sees it's happening, they stop sending, then we can recover. With wireless, these two nodes are sending, but neither node can hear one another, so the collision goes on for a long time. This wastes more of the link, it's more inefficient, so that's why it's a problem. So now we need to solve these problems. We know that wireless is more complicated than wired. What can we do about it? I'll tell you about a possible solution, which is quite influential, and that solution is something called MACA. I think it stands for Multiple Access with Collision Avoidance. You don't need to remember that. MACA is actually not quite what's used in 802.11. 802.11 uses a refinement of MACA. But going over MACA will give you a sense of just how these issues can be handled if you're designing protocols, and it'll help us understand what 802.11 uses. The idea in MACA is that since we have these problematic scenarios, instead of simply sending the frames directly and maybe encountering them, we're going to use a short handshake between the sender and receiver to find out what's going on, make sure it's okay. Here are the rules for MACA with that short handshake. Okay, step one here. The sender simply sends a small frame called a request to send. That's very short, like about an acknowledgement frame. It's not a big data packet. It sends that request to send to the receiver. The request to send also includes a frame length, so it tells you how big a frame the sender wants to send to the receiver next. The receiver, when it gets this, replies with a clear to send. That's simply another short packet saying, okay, yep, coast is clear, I'm expecting your frame, go ahead. Fine, we've just sort of added a bit of preamble. And then, after all of this, the sender simply transmits the frame. That's it. The interesting part, however, is that nodes that heard the CTS stay silent while the sender transmits the frame. They can do this because the RTS and CTS include information about how long the frame is, so the nodes that hear the CTS know how long to be silent. And this is the key addition of MACA that's going to solve some of the problems. We'll see how in a minute. It's true that the RTS and CTS are just sort of like short frames, and as we send them we could run into some of these same problems. But the RTS and CTS are much shorter relative to packets. They might be 100 or 1,000 times smaller. And in this case, the collisions, since they're a lot shorter, are just less likely, so we run into fewer problems. So let's see how MACA solves some of these problems. First of all, hidden terminals. Let's suppose that A wants to send to B, and C is a hidden terminal that might interfere. Okay, first of all, A sends the RTS, here it is, to B. That should be received. Yeah, I've shown that. Next step, B is going to reply with a CTS to A to say, okay, go ahead. B sends a CTS to A. Great. Of course, that transmission, since we're in radio range, will also be heard by C. Right? Now, C at this stage will say, oh boy, I didn't hear a request to send. You know, so maybe, since you didn't hear that, you didn't know anything was going on. But luckily, C did hear a clear to send. So C knows that something is about to go down, even though it didn't hear the request to send. Here's that picture cleaned up. So you can see C's now in a state of alert. It knows that someone's going to use the wireless. Now, A simply sends to B. C, because it heard this clear to send, defers or just waits for this time period to pass so that the transmission from A to B would be successful. Great, we solved hidden terminals. What about exposed terminals? Now, B will send to A and C will send to D, and we want them to both be able to send in parallel. Step 1, B sends a request to send to A, C sends a request to send to D. Now, of course, B's request to send will also propagate to C, and C's request to send will also propagate to B. Neither of those nodes will probably hear the request to send because they're transmitting at the same time, so they can't also receive. Next step, we've got the request to send there. We'll also send a clear to send. A gets the request to send intended for it, and it's going to reply to B with a clear to send, saying, yep, go ahead. Similarly, D is going to send its clear to send to C and say, yep, go ahead. Now, observe that the clear to send from B doesn't make it to D. B only hears one clear to send. Everything's good. Similarly for C. So they both get just one clear to send, and this tells them both that they can both go ahead. Here's what happens. Here's just the diagram cleaned up. According to the protocol, they've sent their request to send, they've heard their clear to send, and there haven't been any problems with either of these messages, so everything's good. So now we simply send. B sends to A, C sends to D. At the same time, because we're in radio range, the signals from C propagate to B, the signals from B propagate to C. So the situation around B and C is a mess with superimposed signals. This doesn't matter though, because what really matters is what goes on at the receiver to receive the signal. Both A and D have clean reception scenarios because the other signals don't propagate far enough to interfere at the receiver. Right? So it's interference at the receiver which is the problem. So here we have no interference. And that's what we want. So we've solved the exposed terminal problem. Now that we know how MACA works, we can move on to 802.11 or Wi-Fi. We've really seen most of the machinery we need to understand how multiple access works in 802.11. So 802.11, of course, is this incredibly popular LAN technology that we use today. It's been around since the 1990s, getting more and more popular. 20 years on, it's near ubiquitous. It's really the Ethernet of wireless. It's everywhere. In Wi-Fi, the way it's commonly used, these clients, different laptops or other devices, phones and so forth, get their connectivity to the internet from an access point. So they're all wirelessly talking to this access point. The access point is typically wired to provide connectivity to the greater internet. The key bit we're looking at here is this multi-access problem of how these different laptops get to talk to the AP. The multi-access problem is at the heart of Wi-Fi. I'll also point out for you just that it's a little difficult even talking about Wi-Fi because many different flavors of Wi-Fi have been developed over time. So if you really wanted to know any details, we have to be clear what kind of Wi-Fi we're talking about. But generally, I'd say all of these different flavors of Wi-Fi have gotten faster over time and added many more features. We'll see just a little bit on some of this. What I'm going to do now is just talk about the physical layer and the link layer of wireless. The physical layer, I'll tell you a little bit about it just so you know. This will relate to some of the lectures we saw on physical layer characteristics, so you should be able to understand some of these parameters. Okay, so Wi-Fi is sending using either a 20 or a 40 megahertz channel of bandwidth on these ISM bands. The bands that the government opened up for unlicensed usage in about 1985. They let anyone sort of make equipment that would use it with some constraints, but no expensive license like a TV station. This led to huge innovation, mostly in the form of Wi-Fi, which has taken off. So that was really a very valuable thing to do. Of the different flavors of Wi-Fi, 802.11b and G, and also N, they're all different flavors of Wi-Fi that work differently at the physical layer. They're the same at the link and high layers mostly. These flavors of Wi-Fi operate on the ISM bands around 2.4 gigahertz, and the 802.11a and N flavors work around 5 gigahertz. So N is capable of working in either one. Now they use a kind of frequency division modulation scheme, frequency division multiplexing scheme to modulate information over those bands. They divide this band 20 megahertz up into many fine channels which are used in parallel. It's actually a form of FDM called OFDM. It's more detailed than we're going to have time to go into. You can read a little bit in your book about it if you'd like. This is for 802.11 G and A and N. 802.11b is mostly the legacy form of 802.11. Now, it's slower, it has some different physical layer details. We're not going to worry about it. When we're sending wirelessly here, the different symbols use different amplitudes and different phases to convey information. Depending on your SNR, you might be able to distinguish more amplitudes and different phases. So you will have many different kinds of symbols, and you can get different bit rates that range from 6 to 54 megabits per second, just depending on your SNR and how many amplitude and phase levels you're using. In addition to this, many other bits are transferred across the physical layer to provide error correction. In wireless, errors are common just because the medium is very noisy because of interference. So we need to use error correction in the form of error correcting codes to be able to even receive packets and sort of clean them up. You might, well, I'm just going to point out briefly, you might well have heard of faster kinds of 802.11 than 54 megabits per second. Various tricks are used, including for some of the fastest kinds of 802.11 using multiple antennas at the same time. This is pretty cool. It's well beyond what we can cover in this class. But if you're interested, you could look at a little article here I recommended. 802.11 with multiple antennas for dummies would give you a sense of what's going on. Let's talk about the link layer, because that's where the multiple access control problem comes up. In 802.11, multiple access is done with a scheme called CSMA-CA. It's a carrier sense multiple access scheme with CA stands for collision avoidance. So it's not quite MACA, but it's a variant of it. And it optionally includes RTS-CTS as part of that, the RTS-CTS we've seen. Although it tends not to be used very much in practice because it's often not necessary for typical Wi-Fi configurations. With Wi-Fi, unlike Ethernet, the frames are acknowledged and retransmitted with ARQ. With Ethernet, we just had a CRC32. If an error was detected, you threw it away. That happened rarely. With Wi-Fi, because wireless is more prone to errors, many packets would be lost if we did this. So the packets are acknowledged, and if they don't get through, they're retransmitted, just to up the likelihood of them getting through. Now I said, just moving on to the third bullet here, that a good thing to do with protocols is to look at the format of their messages to see what's going on. If you do this for Wi-Fi, you'll see pretty funky things with the addressing. Most data frames are going to have 3 addresses on it. It's kind of weird. You'd usually think of a source and a destination. What's going on here is that 802.11 heavily involves the AP. So we actually have 3 addresses identifying a source and a destination and an AP that's potentially in between them. Although, often the AP is really the destination as well. Errors here, as well as the AXN transmissions, we have a 32-bit CRC just to sort of detect residual problems. And there are many, many more features you could read about for Wi-Fi that I'm not going to go into, but I'll just mention by way of example that these features include encrypting the contents of the frame so you can't read what's there, and other functionalities such as power save functionality, so devices can tell the AP that they're going to sleep so they can save on their battery. Okay, finally, let's look at this 802.11 CSMA CA scheme for multiple access to see how it works. It's somewhat simplified compared to MACA. So multiple access control is a subject which hasn't really been definitively solved for wireless. And there are different variations around and they sort of work okay, but none of them are quite ideal. And so this is just what 802.11 does as a reasonable trade-off. Instead of using RTS-CTS most of the time, you can optionally do that as well. What 802.11 does is it avoids collisions by inserting small random gaps instead of an RTS-CTS. If we have these small random gaps, that's why you don't need RTS-CTS always. So in this scenario, we have a timeline here. Time is just going from left to right across the page. And we have timelines for 3 different senders, A, B, and C. A is going first. A is just sending a data frame. And there's also going to be an ACK after that, because that's how this wireless works, unlike Ethernet. This data is going to D, some other node that's not shown here. Now let's suppose that B and C both want to send while A is sending. Where you can see here, B is ready to send its packet, but it uses CSMA, it senses the medium and it hears A. A must be talking to the AP or something. Similarly, C was sending. Not sending. C became ready to send while A was sending. It heard A. So both B and C are waiting to send. Eventually A is finished. Its data frame and ACK frame is done. What happens? If we just sent right away, as is the case with Ethernet, we would run into a collision. We would waste a lot of the medium. It would be a problem. Instead, both B and C insert small random gaps. Here's a small random gap. C inserts this random gap, waits. After this much time has gone by without anyone else using the medium, C sends its packet here. There's the data frame, followed by the ACK. B happened to choose randomly a slightly larger day, even though it was ready first. Everyone picks a random one and its roll of the dice was bigger. It waited this long, and then it stopped here simply because it heard that C was sending, so it suspended its timer. After C was done, it continued counting down its timer up for this small random interval. When it expired, here B got to send its frame. And in this fashion, by inserting these small random gaps, just to sort of test and allow someone else to use the medium and see who's waiting to send, B and C, even though they both wanted to send, have ordered themselves and they both got to send their frame. These back-offs are sort of wasted time, idle time on the air. And this is the cost of using wireless. But these back-offs are small relative to the data frames in duration. So we do okay in wireless. And finally, just to wrap up 802.11, let me just talk a little bit about some of the future trends for 802.11. 802.11 is a key technology, so I thought it might be interesting just to do this. Now, I don't really know what's going to happen with 802.11, of course, so this is just a guess. Firstly, it's likely that 802.11, well, it's already ubiquitous. It's likely to become more ubiquitous. Really, all devices these days seem to have an 802.11 NIC for wireless connectivity. What's likely to happen here, though, is that we'll have greater diversity. You can have very fast computers, high-end computers, and very low-end computers, your wristwatch or whatever, can all have Wi-Fi and all want to use the same AP. So now the nodes are not generally equal in capability like a laptop. Some are more powerful, some are less powerful. That will affect the protocols in small and subtle ways. We can also expect a lot of innovation. Everyone wants to be able to send more information across Wi-Fi. It always seems to be getting faster. This is likely to continue, and maybe more so than simply getting faster, Wi-Fi is likely to get more power efficient, so that the nodes that can use it, if they're battery operated, don't deplete their batteries so quickly. This kind of innovation is very much driven by physical layer technologies. As these technologies advance, Wi-Fi just sort of gets better, even without the MAC layer changing very much. And finally, I'd point out right now that Wi-Fi is a bit of a hassle to use. It's quite manual in terms of identifying what access point you can use, for which you have credentials, typing things into web pages and so forth. It's also a little limited in that transmissions go through an AP even when you have two devices in the same room most of the time. It's often more easier to use something like the cloud Dropbox or something to exchange files than Wi-Fi, even when your devices are in the same room. That's just wrong in some sense. So we're likely to see more seamless integration of Wi-Fi into the massive connectivity that devices have. Then people would have to be less involved in setting up and configuring Wi-Fi. This is likely to happen over time. Okay, so now you know about Wi-Fi.